Hi everyone, I'm Andre from ICRA Perth, and I'll be talking about misalignments between stellar and gas rotation in the nearby universe and what they can tell us about galaxy evolution. And I'll focus on the physical processes which are causing the misalignments and on the galaxy properties which are driving the likelihoods and time scales of these configurations. Now, stellar and gas kinematic misalignments essentially refer to cases of galaxies where the stellar and the gas components are rotating in two different planes which are offset from each other by a given angle, as you can see in these two nice polar ring galaxies here. And this angle can take essentially any value between 0 and 180 degrees, going from a co-rotating to a counter-rotating configuration. Now, in terms of what physical processes are causing these types of configurations, we can broadly class them into two categories. We can have the ones which involve gas accretion and cases which involve gas being expelled from the galaxy. Now, gas accretion can come from a number of sources. We can have cold accretion from filaments, which is more significant at higher redshifts. We can have hot accretion from a galaxy's outer halo, which is more significant in the nearby universe. Alternatively, we can have a galaxy interaction, so something like a flyby, as you can see here, or a gas-rich merger. And on top of this, galactic outflows, especially AGN-driven ones, may result in an observed kinematic misalignment between the stellar and gas component. And with a lower occurrence rate, gas stripping in the cluster environment may cause these configurations as well. Now, typically in observations, the assumption is made that when we see a misalignment, this is exclusively caused by gas accretion. And what I'm going to discuss in this talk is ways that we can disentangle these different physical processes and separate these two categories in observations. And once that's in place, we can focus on our accretion-driven misalignments, which essentially gives us a sample of galaxies where the gas has an external origin. And with this, we can address open questions such as whether or not the newly accreted gas is feeding new star formation or not, or what galaxy properties are dominating the timescale that the gas takes to process into a stable configuration. Right, now when studying kinematic misalignments in the nearby universe, the SAMI Galaxy Survey gives us a very good sample, with the final data release providing resolved kinematic maps for just over 3,000 galaxies in the group, field, and cluster environments. And these galaxies are spanning a wide-ranging stellar mass and morphology. This is an example of such a galaxy, and the way that we quantify the misalignment is through what we call a kinematic position angle, which is essentially the direction in which each baryonic component, the stars or the gas, rotate in projection. And we use the combination of a parametric and a non-parametric method for computing these position angles to account for all possible cases. Now, in our study, we started from the entire SAMI DR3 sample, which is the final data release of SAMI. We implemented a number of quality cuts to single out the galaxies with reliable kinematics, which puts us at just over 1,400 galaxies, for which we compute both stellar and gas position angles. And this is the parent sample for our study. From these, we select our misalignments, which are essentially objects where the kinematic offset between stars and gas is larger than 30 degrees to account for our measuring errors. And with this in place, we're in a position where we can start looking at how the physical properties of misaligned and aligned galaxies differ. Now, what I'm showing you here is my misaligned sample in purple on the star formation rate stellar mass plane in comparison with our parent sample in green. And the immediately obvious thing is our misalignments are preferentially scattered well below the main sequence in the higher stellar mass range of the parameter space, so above 10 to the 10 or so solar masses. Similarly, on the Sersic index stellar mass plane, again, what we notice is our misaligned galaxies have preferentially larger Sersic indices, and this is single component R-band Sersic index, I should say. And this whole picture is consistent with a scenario in which misaligned galaxies are preferentially quenched early types. Now, all of these objects, misaligned galaxies, have a rotating ionized gas disk. And from this, one might expect that star formation may not be the main source of ionization for the gas. This is the next aspect that we looked at. And we've classified our misaligned galaxies spectrally into star-forming liners and Seyferts using a combination of two emission line diagrams, the N2 and S2 BBTs shown here on the left and right. And we've given more weight to the N2 BBT when separating our star-forming population, which are the blue dots. And we've used the S2 BBT to separate our liners and Seyfert populations, as these have been shown to be easily distinguishable on the S2 BBT. Now results show that only 22% of our misaligned galaxies have their ionization driven by star formation. 61% are classified as liners, so all stars in the central region ionizing gas, and 17% have a significant AGN component. And what this suggests is that, at least for the accretion-driven misalignment, gas accretion is not feeding new star formation in most cases. Right, now if you combine the information on the spectral properties of the galaxies with the measurements of the kinematic position angle offsets and the optical imaging at our disposal, what we can do is disentangle between the different physical processes that cause the misalignment. And what I'm showing you here is my misaligned sample, again on the star formation rate stellar mass plane, color-coded according to the most probable cause of the misalignment. And we've identified 4 main processes, and I'll do a quick walk through each one of them, if this comes back. Oh, there we go. We've got our outflow-driven misalignments, which are essentially the Seyfert objects which are not counter-rotating, shown in red here, and they make up just about 8% of our misaligned sample. We've got our tidal interacting objects shown in yellow. These are identified based on the clear features in the optical images, and they only contribute to about 3% to our total sample. And we note that for all these objects, the misalignment is always lower than about 90 degrees or so. Right, next we've got our merger-driven misalignments, and these are either merger remnants or ongoing mergers, and they can produce a kinematic offset of essentially any value across the whole range between 0 and 180, and they contribute to 15% of our sample. And finally, we've got essentially everything else. These are the galaxies where we think that the kinematic misalignment is due to gas accretion from either filaments or the outer halo, or potentially even a past merger that we can't see anymore in the optical image. And these are about 3/4 of our sample. Now from this, what we can do is we can take away our outflow-driven misalignments and focus on the accretion-driven cases and move on to the last bit of our analysis, which is looking at what are the dominant galaxy properties that are driving the likelihood of misalignments and their timescales. And we are looking at, well, you can't really see all the title, but essentially we're looking at 2 key properties which are expected to drive these processes, which are galaxy morphology and specific star formation rate. Now, what I'm showing here is the distribution in Sersic index for our misaligned and parent samples in green and purple. And the immediately obvious thing is misaligned galaxies typically have much higher Sersic indices. However, part of this trend will be due to the 2 samples having different distributions in stellar mass and star formation rate, right? So what we want to be comparing our misalignments with is a control sample of aligned galaxies matched in stellar mass and star formation rate. We've computed such a sample, and this is what it looks like in orange. So part of the discrepancies have reduced, but the distributions are still statistically different, essentially, with misaligned galaxies having larger Sersic indices. Similarly, for specific star formation rate, we see that misaligned galaxies shown by the purple histogram here have much lower specific star formation rate in general. And then again, what we want to be comparing them here, as opposed to the parent sample, is a control sample of aligned galaxies matched in morphology and stellar mass. We compute such a sample, and again, it's shown here by the orange histogram. And similarly to before, some of the discrepancies reduce, but the distributions are still very much statistically different. And this seems to indicate that misalignments are more frequent or longer lived in galaxies which have larger Sersic indices and lower specific star formation rate. Physically, what this means is if we've got a galaxy and gas gets accreted with a misaligned angle, the stellar component exerts a torque on it. This torque is lower if the galaxy has more centrally concentrated stellar mass, so higher Sersic indices. And also, if the galaxy has a lower gas fraction to begin with, it's got a less component to interact with. So it stays in the misaligned configuration longer. So just to summarize our results, we've looked at the main physical processes which are causing misalignments and found out that these are caused by outflows in about 8% of cases, by gas accretion from either a recent or an ongoing merger or a tidal interaction in about 18% of cases, and by accretion from any other source in about 3/4 of the times. The accreted gas does not seem to be fueling new star formation in most cases, and the time scale of the misalignment is driven by an interplay between bone morphology and specific star formation rate. And there doesn't seem to be a dominant component between the two. And I will leave it there. Thank you.